I think more or less anybody that wanted to join would have joined already. So I'll just go ahead and start here. Okay, so welcome everyone to the mock paper review. The next 1.5 hours will be spent on going through the papers, not just the solutions, but things to look out for. And hopefully at the same time, I'm able to give you a brief recap on more key concepts that I feel would be more important pertaining to your O levels itself. Okay, so for those that have joined the previous sessions, you might have heard this. But for those that are new, okay, just a quick introduction to Overmark. So Overmark, we're actually a team of private tutors. We're hoping to build a student-centric platform that will be focused on helping you out academically and also at the same time, provide sort of like this helping hand and guidance because ourselves, we just been through the education system ourselves. So what we're really hoping to do is to make life easier for you. So that's why we're having this session. Hopefully it helps, okay? And we'll be more than happy to guide you along. Okay, if not, more about myself as well, I mainly do chemistry and physics. So for those of you that attended the chemistry session on Tuesday, and you see me again, that's the reason why, because I do both chem and physics as well as combined chem physics. So I've been teaching for quite a while. So in the next 1.5 hours, I'll be sharing some of my knowledge and some of the things I observe with students. For example, where are the commonly made mistakes and what are certain areas that you might want to look out for. So those will be the things I'll be sharing. As usual, pay attention, jot down as much notes as possible. Okay. If not, we'll go by a very simple format today. We'll first take a look at the paper 1. We'll take a break. We'll take a look at the paper 2. I'll give you all some general exam tips for O levels because right now it's in September, right? We are 6 to 7 weeks away from our first major paper. Then I'll also give you a bit of a sensing of how you should do your revision, and we'll open the last part up to Q&As. Okay, the Q&A can be anything about the paper. It could also be about revision or any exam tips or anything of those sorts. Okay, so feel free to ask. I'm just here, so have no worries. Okay, if not, I'll get everybody to bring out your paper. Let's take a look at the first paper together, shall we? Okay, same thing. If you have questions, just head over to the chat. Okay, I'll check it from time to time. Okay, if not, let's just jump straight into the paper. So for this paper, there's obviously going to be 40 questions. I'll highlight which are the more tricky ones that I want you to pay more attention to if you're intending to relook at this paper again. Okay, for question 1, I feel like this question, if you've gotten it right, it shows that you have a very strong understanding. Obviously, this is about your vernier caliper. But the thing I need you all to remember here is that when we are dealing with zero error, especially when we are talking about negative zero error, we have to calculate from the back. Okay, so I'm just going to draw some reference from the curated notes because I need some of the content here to supplement what I'm saying. But most importantly, as we are looking at zero errors, okay, I think positive zero error, most of us, we are fine, right? We know that, okay, positive zero error, I subtract my positive zero error. But for negative zero error, I think it's a very commonly made mistake that students think of this as negative 0.08 zero error. But rather, if it's a negative zero error, you should be calculating from the back, right? So instead of 0.08, this is actually negative 0.02 zero error. And how do we correct a negative zero error? We subtract that negative value. Essentially, we plus it. So if you go back to the paper and you take a look at this question, take note that the smaller rulers on top, while the main scale is below. And you see the 0 here, this is ahead of the main scale. This implies a negative zero error, right? And which line is a line? It's actually the third line here that's a line. So instead of 0.03, it should be negative 0.07 as our zero error. Then you look at diagram 2 for the actual reading. Then you correct your zero error. That's how you get B as the answer. Okay, so if you've gotten this question wrong, I strongly encourage you to spend some time to go and recap on not only your vernier caliper, but your micrometer screw gauge as well. Okay, question 2, this is a free mark here. Which one is not a vector quantity? Speed is obviously not a vector quantity. Velocity is its vector quantity equivalent. Okay, I hope I don't have to explain this. Vector means magnitude and direction. Okay, question 3, what I want you to take note here is more of an exam technique. Assuming the question is a kinematics related question and the question doesn't provide you with the graph, I strongly encourage you to draw out the graph, okay? Because drawing out the graph gives you a very good chance of making the correct analysis to solve the question. In this case here, we are required to calculate average speed. So the formula here is total distance over total time. If you draw out your speed time graph, then it becomes quite easy to recognize that, the area underneath the graph gives me my distance. Then you just divide it by total time of 10 seconds. You should be able to get your final answer, okay, 3.8. Okay, so the major takeaway here is that if you come across such a question, my tip for you is to draw out the graph. Okay, question 4, terminal velocity. Okay, so terminal velocity, while most of us understand the concept of it, okay, how detailed do we know this? This question that you see here is quite closely mirroring a lot of prelim as well as O-level papers questions itself. So what you need to know about terminal velocity is not only the fact that it's traveling at a constant speed while falling, there are certain things you want to look out for, particularly understanding that the resultant force is zero. Okay, why do I claim that this is important? It's because when we are studying terminal velocity, it is common knowledge that, the velocity will even out. Okay, but what I need you all to recognize is how do we explain and justify terminal velocity is when the air resistance is equal to the weight and resultant force is zero, therefore there is no acceleration. That's why you get this constant velocity, which we call terminal velocity. So this is really going down to the detail of how well do you know your terminal velocity. So for something that's traveling at terminal velocity, resultant force must be zero. Okay, an object with, I'm just talking about A, an object with greater mass does not have a greater initial acceleration. Your initial acceleration is irregardless of your weight, is depending on gravity. And all objects on Earth experience the same amount of gravity. So in fact, all objects experience the same initial acceleration. So statement A is not true. Okay, statement D is true. Okay, so this is for terminal velocity. Okay, we got a quite relevant question here. If resultant force is zero, okay, the object is not moving. Now, when we say an object, right, if an object is at rest and it experiences zero resultant force, yes, it would remain at rest. But for an object that's already moving, zero resultant force just means it will continue to move at a constant velocity. Because here is already moving, there's no external resultant force slowing it down or speeding it up. So your object will just keep moving and moving. Okay. Not too difficult analogy here is you think of a bowling ball. Okay. After you throw your bowling ball and it's rolling down the lane, right? There is, assuming there's no external resultant force, right? Assuming that there's no force acting on it, because assuming it's a frictionless surface, your ball will just keep rolling and rolling and rolling, right, at constant velocity. It will not accelerate, but it will not stop as well. Okay, this is by the condition that resultant force is zero. Okay, so I hope I clarified that. Okay, in this case, okay, what if it's accelerating? There needs to be a resultant force for it to be accelerating. Okay, if not, let's take a look at question 5. Okay, question 5 is a classic question. If you want, you can put an asterisk here. The reason I say that is because when we see the term constant speed, okay, our initial thought might be kinematics, right? Because we talk about speed, constant velocity. But the truth is, the reason why constant speed was mentioned in this question is because they want you to recognize that when something is moving at constant speed, acceleration is zero. What does this imply for the resultant force? If F equals to ma, right, where F is resultant force and acceleration is zero, your resultant force would naturally be zero. Therefore, answer should be A. Okay, so it doesn't really matter how heavy the diver is or how much his gears weigh. If the speed is constant, it means acceleration zero, resultant force will be zero. Okay, so this is quite a classic question. Okay, so if you see this question, don't be tricked or don't be led in a separate direction. Okay, it's not V minus U over T here. Okay, this is a question about resultant force. Okay, question 6 is just very straightforward. Property of an object to resist change. This is referring to inertial. If you're ever coming across a question on inertial, it's straight away just mass. Okay, not weight, because weight can change on different planet. It's just about the mass. Okay, question 7 is about the Mercury Barometer. Okay, when atmospheric pressure decreases, the pressing here is less mercury will go up the column. Yes, the height of the mercury column will decrease. So number 1 is true. When we tilt it sideways, the vertical height remains unchanged, because this 76 is the vertical height. Even if you put it like that, the mercury will still be here, because all we're caring about is the vertical height. Okay, 1 unit of atmospheric pressure is equivalent to 76 cm of mercury. This is accurate. This is essentially what the Mercury Barometer is showing us. Okay, and in part 4, if a gas present in the test tube, there is gas here, instead of a vacuum, there is gas pressing down. Yes, the height of this would decrease. So all 4 statements are true. Okay, answer should be D. Okay, next. Question 8 here. This is a question obviously about moments. So I know we are very used to anti-clockwise equals to clockwise, but you need to realize that not all questions is in a state of equilibrium. So in this question here, there is actually a resultant moment. What does this mean? It means that when you play around with clockwise and anti-clockwise, one value would be bigger. Okay, so you'll notice that if you take force times your perpendicular distance and force times perpendicular distance, you will have an excess of 40 Newton meter in the anti-clockwise direction. Okay, so the whole object is actually turning more this way. Okay, because maybe larger force times perpendicular distance. Okay, so straightforward, whenever we're dealing with moments, just remember is force and perpendicular distance. All right, then you'll be fine. Question 9 is a trick question. If you've gotten this wrong, it's because you assumed and you did not read the question carefully. Which portion, okay, is in this keyword here, accelerates up the slope? In a normal setting, typically when something gains GPE, you will assume that they lose KE, right? So if you put your answer as A, it might not be surprising. But what I need you to recognize here is that the system's amount of energy here is not a fixed amount, because the person that's riding the bicycle is doing work, he's supplying energy. So kinetic energy increases because if acceleration is occurring, your velocity increase, your half mv square will increase. So kinetic energy should be increasing. And obviously, since it's going up the slope, his GPE will increase. Therefore, answer should be B. Okay, so my tip for you here is to read the question carefully. Don't assume anything. Okay, so that's the reason why question 9 answer is B. Okay, I got a question here from Vanessa about question 8. So you're saying that shouldn't it be clockwise, as anti-clockwise is more, so it needs to go clockwise to ensure equilibrium. Okay, now take note that there is no part in the question here that mentions equilibrium. This beam right now is not in equilibrium. There is one side that's heavier. They're asking you which side is heavier by how much. Okay, so be comfortable with this idea of resultant moment. I know what you're referring to, right? Because normally we will assume that the beam is in equilibrium. Everything is perfectly balanced, right? Then we just need to find the unknown figure. But here, we're just saying that it's pivoted on this point. We are saying that it will turn a certain way. It might turn clockwise, it might turn anti-clockwise. We don't know which way, and we also don't know how much. So we're just trying to find that out. Okay, this is not about equilibrium. Okay, even though most questions are about equilibrium. Okay, so just take note of that fact. Okay, if not, let's move on to question 10. Question 10, just take note that when we are doing power, you should know that power equals to work done over time. Or you can also think of it as force times distance over time, right? Okay, so what is this force here? Is actually the mass of the driver plus the package, but mass alone is not a force, right? Because mass unit is kg, right? So instead, it should be W equals to mg. So that's where we get the 85 times 10 is actually 850 newtons. Okay, so that is your force, 850. Okay, how much distance does it cover? We only care about the vertical height, right? Because it's going up a flight of stairs. So you want to times 30. Okay, if you divide by 2, you will get 9380. Wrong. Why? 2 is 2 minutes. Okay, the moment you see minutes, you need to be on high alert, right? Because we, as physics students, we know that the unit of time is seconds. So we have to convert the 2 minutes to 120 seconds. That's how you get the answer as A, Okay, so power will also come up again in electricity. I just need you to ensure that whenever we're dealing with minutes, you always convert it to seconds. The only time you don't convert it to seconds is when we are playing around with kilowatt per hour. Okay, if not, anything in physics is per second. Okay, I emphasize that. Okay, question 11. What is this phenomenon where your smoke particles are moving about with bright specks of light? Okay, what is causing it? Okay, is the uneven bombardment by your air particles. This is not about your particles moving randomly. Okay, what we see is the random movement of the smoke particles. But what is causing it is because the air molecules are bombarding it unevenly, causing it to turn this way, turn that way. That's why you get this random specks of light via the reflection of the smoke particle surface. So think of it as like this smoke particle that's constantly rotating and traveling in random directions because the air particles are punching it in random directions. Okay, that's why you get a constant random motion. All right, so that's Brownian motion for you. Question 12. Okay, here I want you to take note of not only how to calculate, but I want you to pay attention. This says 500 grams, right? Do you notice here it says kg, right? Then again here is about kg. Kg, kg. Take note, this is kilojoules. So really the difficulty for, I would say, for calculation for specific capacity and things like that is really not so much the theory. I think it's quite obvious because we already know that Q equals, I assume you know that Q equals to MC delta theta, right? We also know that Q equals to MLF, which is latent heat of fusion, or Q equals to latent heat of vaporization. I think we are quite comfortable with the formulas here. But if you are making mistakes, it most likely is going to be about the fact that your units are off. Okay, so this is what I need you to take note of. Okay, yes, I think one of you highlighted that the specific capacity of water is 4200. Yes, that is correct. But if the question gives you this value, you use this value. Okay, so I know that the correct value that we are comfortable with is that. Okay, but just give what the question provides you with. Okay, because the water here might not be, it depends lah. So you just follow what the question gives. Okay, so if not, I think the calculations already stated here. So I think the value should be fine. Okay. Okay, so why is there latent heat of fusion? Okay, there's latent heat of fusion here because what you're starting off with is ice, you see? So you need to first convert your ice from negative 0 degrees Celsius. Okay, so there's a few steps here. So from negative 20 degrees Celsius to ice, you need to convert from this to this first. Still ice, right? So this is why we use the specific heat capacity of ice. So this is why we take the 0.5 kg times the specific capacity times the change in temperature. So MC delta theta. Now my ice is at 0 degrees Celsius. What do? I need to melt my ice into water. My water will still be 0 degree. This is when latent heat of fusion comes in. What do I need to do next? I need to turn my water from 0 degrees Celsius to 100 degrees Celsius. This is when I use the specific heat capacity of water. So once again, MC delta theta. Okay, this is this one. Okay, then lastly, to turn my 100 degrees Celsius of water into gas, I need to use the latent heat of vaporization. This is the last working here. When you add all of them up, that's how you get your answer. Okay. If the values really do not tally, then maybe it's a calculation on my end. Let me double check. Okay, but the method is correct. Okay, I think that's most important. Okay, I'll go and double check this question later during the break. Okay, if not, let's move on first to question 13. Okay, so here, which one is incorrectly matched? Okay, so this one you just need to know your thermometric properties. Okay, okay, we got a good question. So maybe I'll double back to question 13. Why is the latent heat of vaporization more than the latent heat of fusion? This is not usually taught in school, but I'm going to spend a bit of time to address this. So for those of you that have the curated notes, you will already know, because here we address that question directly, specifically when we compare the latent heat of fusion with the latent heat of vaporization. You'll always notice that the time to melt is always shorter than the time for boiling. Okay, why is that the case? It's because in order to change something from liquid to gaseous state, we are moving it from loosely packed to far apart. So we need to completely overcome the intermolecular bonds. This requires a greater amount of energy. Okay, and when we turn from liquid to gas, the increase in volume is also more substantial. So it's always more drastic to turn from liquid to gas, which is why we always have a greater value for latent heat of vaporization. Okay, so this is something that is not taught in school. You might want to take note of. Will it be really tested at O level? I hope not, because most people won't be able to answer. Okay, but I think that's a very inquisitive question from Alicia. So I thank you for asking, and everybody get to learn at the same time. Okay, so it seems like the correct answer for question 12 is 1.4 times 10 to the power of 6. Okay, so I'll double check on that. So just give me some time. Okay, if not, let's go back to question 13 first, yeah? Yes, latent heat is the part of the graph where it's flat, where it's undergoing a change in state. Okay, incorrectly matched. Okay, so how many thermometric properties are we required to know? For this, we need to go all the way back to our chapter in temperature. So we see here in this table that there are 3 thermometric property and their respective thermometers. So if you know this table well, okay, then you should be able to answer that thermocouple is not about the current, but thermocouple is specifically about the electromotive force. Okay, so you need to be able to match the thermometric property with the thermometer. That's how you'll be able to solve question 13. Okay, question 14. Okay, average speed, frequency of collision, pressure. Here the question is stating that when it's heated up and kept at constant volume, okay, how does it change? If something is heated up, the average speed will definitely increase. It will collide with the wall more often, and the pressure would naturally increase because the force per unit area increases. Okay, so that's the answer for question 14. Question 15, this is one of my favorite questions. If you want, you can put an asterisk here as well. I think this question is important because we know that the ideal gas law is pressure volume is proportional to temperature, right? So what is going on here, right, is that the pressure is constant. Temperature is increasing. What happens to the volume? Volume increases. Okay, now let's talk about the facts one by one. The moment you see something is heated, right, the speed can only increase. Okay, so the speed is directly correlated with the temperature. So as long as something is heated up, your molecules will move faster. Okay, but we know that if your molecules move faster, by right, your pressure should increase, right? Because there is like more collisions, it's colliding harder, you expect the pressure to increase. But how does the pressure remain constant, right? What allows it to remain constant when temperature is actually increasing is by virtue of increasing the volume. Because when we increase the volume, now there's lesser particle per unit area, the rate of collision would decrease. So what happens now is that the molecules, they are colliding against the piston. When they hit, right, they hit hard, but they do not hit as often. So when we are talking about force per unit area, it depends on 2 things. How often do they hit? And when they do hit, how hard do they hit? So in this case here, pressure is constant because they hit harder, but they hit less often, which is why the pressure is able to remain constant. Therefore, answer here should be B. Okay, you can find a similar question in your 10-year series as well. Okay, but this is one of the main questions that I find is a bit more difficult. Compared to 14, I think 14 is a lot more straightforward. 15 requires you to really wrap your head around the concept. Okay, so yes, some of you have quite relevant question in terms of, then we increase the speed, shouldn't it collide more often? You need to consider now that because the volume has increased, there is imagine the particles, right? Last time, maybe they bang against the piston once every second. But now, because the space is so much bigger, they collide against the piston every 2 seconds. It collides less often because now the volume is bigger. Okay, so you think of it, if you throw a ball in the room, right, and your room is very small, the ball is going to bounce against your wall multiple times in the same period of time. But now, if your room is a lot bigger, it's going to bounce against the wall lesser number of times. And that's the reason why it compensates for the increased speed of molecules. Okay, you get it? So faster, in If it's within the same volume, then it will collide more often. Okay, so that's under the assumption that constant volume, then that's the case. Okay, seems a couple of you seem quite confused, right? Let me just quickly scroll to the notes, right? And to show you all the exact portion why this is the case. Okay, so the situation where you are confused, okay, not you all, but some of you are confused, is assuming that it is at fixed volume. Then when we increase the temperature, we will increase the frequency of collision and the force exerted because now the particles are moving faster. This is true, assuming constant volume. But the situation that we're playing with now is assuming constant pressure. So I'm talking about the second scenario here. Assuming pressure is constant, an increase in temperature will increase the volume. Okay, so I see, so when we increase the temperature, yes, it increases the frequency of collision, but how do we keep the pressure constant? In order to reduce the frequency of collision, to maintain a constant pressure, the particles per unit volume has to decrease. And how do we achieve this? By increasing the volume. So this would decrease the number of collisions. Okay, so I hope this is clearer. Okay, if you're still stuck, okay, I highly suggest you go back to your ideal gas law to revisit this. Okay, because I'm talking about this question for 5 minutes already. Okay, but that's why it's difficult, and why there's asterisks. Okay, I hope I explained it as best as I could. Okay, it's because the volume here is not constant. Okay, let me write this down. Volume is not constant, so don't be mistaken. Okay, what you are saying is true, assuming volume is constant. But volume is not constant, rate of collision actually decreases. Okay, question 16, I think is pretty straightforward. The freezer compartment is usually at the top, so cold air sinks. Okay, the air particles will not change in size. Okay, it is the fact that they move closer, that's why they become denser, that's why it sinks. Okay, so answer here should be C. Question 17, boiling and evaporation. This one is pretty straightforward. Okay, which is true? These two are true. Okay, so when you're studying for this, right, make sure when you're revising, you test yourself, right? What are some similarities and differences between boiling and evaporation? So you should always take a look at this table. Okay, some versions of it, whatever your school has, probably it will outline the same thing. Okay, so just make sure you get this right. This is 3 marks. All right. Question 18, right? Which block has the highest specific capacity? So here, I just need you to know, you just need to do MC delta theta, right? The Q is constant, right? So you just need to play around with your values. The one with the largest mass, okay, times temperature. Okay, you see here, right? If you go and calculate the value, right? 4 times 24 is 24. 25. 24. This is 21. The one that has the smallest value here has the highest specific capacity. Okay, if you're wondering what's the formula, we're playing around with this. Right, then since Q for everything is equal, how do we find C? C is essentially Q divided by M delta theta. So the smaller your denominator is, the greater the value of your C. Okay, so this is about formula manipulations. Okay, so you just need to know the base formula and then you put it in the context of the question. Okay, so next question, question 19. If you want, you can put an asterisk here as well, purely because this question is quite commonly tested. How often exactly? It has appeared around 4 times in the last 10 years. So if it appears in your exam, don't be shocked. All right. How do we do this question? We note that when water travels from shallower to deeper range, the speed increases. Okay. So here we see that there is 1 wavelength, 2 wavelength, 3 wavelength, right? So 3 complete wavelength over 9 cm. So if we use V equals to F lambda, your lambda here is 3, your V is 12. I can find out that my frequency is actually 4. Frequency remains unchanged. So if I use V equals to F lambda again, my frequency is unchanged. My speed is 18. So how much is my wavelength? You should be able to get B, 4.5. Okay, so this one, I warn you already, if it appears, either you are thanking me or you're hating me. Okay, you thank me if you remember this session and you go and practice this more often. Go and flip through your 10-year series. It came up 4 times. Okay, so just be very careful when you're doing this question. Okay, for question 20, whenever we see a light ray diagram, I need you to do one thing first. Okay, that one thing is to draw in the normal. No matter what question you do, if it's light, just draw in the normal. Okay, if the normal is not given for you, right, given to you, draw it. Okay, why is this important? It's because the moment you draw in the normal, you know that this is 30 degrees, right? Because this is 90, 120, 30. Then this angle here is 50. You need to remember that the 40 here is not important because the angle that we're always playing around with is between the light ray and the normal, right? So questions will trick you. They always give you this 40 degree because they're being annoying, right? Then some students will really use the 40 to go and solve the question. That's when they are screwed, right? Because they are not using the correct angle. So if you ever see a light ray diagram, check for the normal and check for not falling for this trick. Okay, it's such a basic trick in the book. Okay, if you made the mistake once in the exam, hopefully you feel the pinch and you remember. Okay, if not, hopefully attending this session helps you remember this. Okay, so don't ever get tricked by using the wrong angle. Keep them in mind. Okay, then all you need to do is to do sine I over sine R. Okay, I know sometimes schools teach sine I sine R, but the truth is it should always be the angle in the air over the angle in the medium. So it should be sine 50 over sine 30. That's how you get your answer 1.5. By the way, your refractive index cannot be lesser than 0. So A will never be an answer. Cool? Okay, so make sure you be careful about this. Okay? Then let's move on to question 21. Total internal reflection. This one you just need to make sure you study it. Okay, these two are true. Okay, now why is statement 1 and 4 not true? I think that's more important rather than these two are true because this one is really in your notes, right? You already know this. Okay, now total internal reflection can only occur when light travels from optically denser medium to air and vacuum. This is not true because total internal reflection can still occur if it's traveling from optically denser to optically less dense medium. That less dense medium does not have to be air and vacuum. It can go from glass to water. It can still undergo total internal reflection. Okay, let us think it for a moment. Even though we are used to comparing it with air or vacuum, it doesn't mean it has to go through air and vacuum. Okay, the reason why statement 4 is wrong is because it's not denser, medium to less dense. It should be optically denser to optically less dense. Density is mass over volume. Optical density is then about the speed of light in your medium. So make sure you're careful, okay, when you're reading, or even if it's a section A question asking you to state the conditions for total internal reflection, I need you to know it's about the optical density, okay? This is about getting your keywords right, okay? Question 22, there are two ways to make a blurred diagram sharp. It's either you move your screen to this position or you use a longer wavelength such that it only converges at where your screen is at, okay? So answer here should be C. Okay, question 23. Here we are talking about lens. Okay, how do we know whether it's diverging or converging? Okay, what you want to do is you take a look at the lens, right? Can you see that if this line goes as per normal, this is how it should behave, but it bends inwards. So this is a converging lens. Okay, and since this converging lens, you can see that based on the path of the light, okay, the light would never converge on the right hand side, which means it will converge backwards on the left hand side. This means it's a magnifying glass setup. Okay, and when we say magnifying glass setup, you know that the focal length should be more than 10, okay, because the object is lesser than f, okay, then it will give you a virtual image. That's why the answer should be D. Okay, question 24. Two notes of different loudness and pitch. This is classic. I won't put asterisks here because it's quite easy, okay? But I think what I need you to recognize here is that loudness and pitch is always tested, okay? Loudness is affected by the amplitude, while pitch is affected by the frequency, okay? So different loudness means different amplitude. Same pitch means same frequency, okay? Since V equals to F lambda, if same frequency, in the same medium, I'll get the same speed. Okay, therefore answer is C. Correct definition for wavefront, then just need to study lah. Answer is A. Which properties is false? Just C, right? Because sound like qualities, properties, this is not correct. Okay, something I want you all to be aware here, right? I know when we are studying EM waves, right, we all know the acronym, right? Like from radio to microwave all the way to our gamma ray. We know that, and we also memorize the functions, right? So we're okay with this. We kind of get this already. But what we tend to miss out is studying the properties of your EM wave. This one is quite underrated. Okay, so you notice here it's supposed to possess wave-like properties. Okay, so not sound-like properties. Okay. Next question, 27 is about echo. So it bounces off here and it bounces off here. So how long does the first path take? On the left side, it takes 1 second. How long does the second path take? It takes 2 seconds. So total time interval here should be 1 second. Okay, like charges repel, unlike charges attract. Attraction here plus repulsion, repulsion. Answer should be B. Okay, question 29. This is another classic question. You want to put an asterisk here. Thank me when it appears in your exam. Okay, so while we are very confident, okay, that we are dealing with R equals to rho L over A, I need you all to pay attention to one thing. Okay, do you notice that the word here is that the diameter is half? Remember, diameter and cross-sectional area is different. Normally, if it's cross-sectional area is half, we just calculate accordingly. It's easy. But when we say diameter, remember, how is diameter related to cross-sectional area? Pi r squared. When I half my diameter, my radius is half as well. So the impact on the area when my diameter is half is actually more. So the area is actually decreased by 4 times when I half my diameter. Why? It's because my A now becomes pi r squared. So when I do rho L over A, my length is twice, so 2L, but my pi r square, right, my R now becomes R over 2 square, which essentially would relate back to become divided by 1/4. So if I write this 2L pi r square, it's like that. Right, so 2 divided by 1/4 is actually times 8. So I times 8 to my original resistance. That's why my resistance of wire Y is 32. Can I? So make sure you get this right. Take note, is it diameter or cross-sectional area? It changes your entire question. If it's diameter, you need to square that. 2R square, half R square, I don't really care. Just make sure you square that change in diameter. Okay, super, super important. Okay, if it appear in your prelims, you know what I mean. Okay, the question 29. Okay, question 30, just need to study. Make sure you know your definition for EMF. Question 31, if you get such a shape, okay, you need to know it's actually your filament length. This is under Ohm's law if you are not aware. So if you take a look at the curated notes, particularly this portion under Ohm's law, you should see different graphs. Okay, so you note that the graph where the IV gives you this kind of curve is actually your filament length. Okay, the one that goes the other way is your thermistor. Okay, and the respective explanation you kind of need to know as well. Okay, but in general, IV graph, this shape is filament length. Okay, you can see here, okay, that the curve is a bit like your math, you know, decreasing gradient. You kind of get the idea. Okay, question 32. This is not a difficult question, but rather I would prefer if you could look at the graph, the circuit. If it confuses you, I highly suggest you redraw it. So I'm just going to teach you a simple way of redrawing. So you always start off at the plus. The moment it splits, you draw a dot. So what I do is I like to draw it like that. I split. When I take the first path, I go through 6 and 4. So I draw it in. Then it combines back. Where did the other path go? It goes from the bottom, right? 5 ohm, then it combines back here. So this is how I look at the circuit. And this to me makes a lot more sense. Okay, now 6 and 4, if they are in series like that, you might as well just combine them to 10 ohm. It's just easier that way, right? Because it's one after another anyway, right? So what do you need to know about a parallel circuit? Voltage across each branch is constant, right? So the top branch will receive 12 volt, the bottom will also receive 12 volt. So if you take a look at the one on top, this first lane, how much is my resistance? 10. How much is my voltage? 12. How much is my current? 1.2. That's how I get my answer. Okay. Question 33. Okay, same thing. You see 4 minutes, your goosebump need to stand. Why? Because it's not 4 minutes, but it's 4 times 60 seconds. Okay, so if the O level you make this mistake, right, you can go and slap, don't slap yourself, but you can be very upset about it, right? Because you're making such a basic mistake. Okay, so remember, minutes, you see it straight away, you remember my face, then you think of 4 times 60 seconds. Okay, so amount of charge, this is pretty straightforward because P equals to VI. After you find your current, you then know that current equals to charge over time. Then you go and find your charge out. So amount of charge. Ta-da! Answer. Okay, question 33. This is obviously about DC circuits. So current, if you recombine it back, the total current is 7 ampere. So how do I find the total EMF of my battery? I already got current, V equals to IR. I just need to find total resistance. So I add these two resistance up first, then I plus 1. Okay, so 1 over R effective equals 1 over 2 plus 1 over 5. You go and find your R effective already, right? Then R effective, you go and plus 1. Why do you need a plus 1? Because there is 1 here. Okay, then after that, you sub it into the IR, you should be able to find your V, which is 17. Okay, I don't think this one should be too big of an issue. If you don't know how to do this, means your circuit is quite weak. Okay, so you might want to go do more practices for electricity. Okay, coming to the end before we go for a short break, question 35, which is true. Okay, statement 2 and 3 is true. LDR resistance does decrease when light intensity decreases. Double insulation don't need earth wire. Okay, that's all. Okay, the other two statements are just not true. 36, cost of 1 kilowatt per hour. So normally what we do is they ask us to find out the cost for the whole thing. But here they give us the cost. So all you need to remember is that the unit of electricity, which is kilowatt per hour, times cost equals to price law. So here your price is $1.20, right? You just need to find how many kilowatt per hour you use to find out what is this unknown cost. Okay, so how do we do so? 3 kilowatt, how many hours? 2.5 hours. So 2.5 times 3. Then you 2.5 times 3, quick math. I cannot quick math. 7.5? Yeah, 7.5. Right. So you just go and find out what this question mark is. That's about it. Okay. Question 37. This is about magnetization by stroking. Okay. How I like you to remember this is the south, you drag all your north here. The north, you drag all your south here. Okay. And then, oh, this one I actually forgot to cover properly. The 3 is supposed to cover the S. South, drag all your north here. So what you get is south, north, south, north. Okay, so answer should be 8. Question 38, DC motor, the nightmare of all students. You're lucky you don't have electromagnetic induction. Okay, but now at least you know that confirm, guarantee DC motor coming up. Like I guarantee plus chalk is gonna appear. Okay, so make sure you go and study this. If you are by now you're still not certain, go and do so. Okay, so how do we solve such a question? You need to use your Fleming's left hand rule. Okay, then you'll know that the left side of the coil is actually going down. Okay, right side is actually going up. Okay, I hope you all don't need me to teach you how to do Fleming's left hand rule. Then coil, because this side is going down, this side is going up, it will turn anti-clockwise. Okay, it experiences the greatest force at the horizontal position. Vertical position means like that. When the north-south like that. No, it's at this position like the diagram, this is where you get the greatest force. When all fields and forces are perpendicular to one another. Okay, split ring commutator will reverse the direction of the current every 1 full rotation? No, every half a rotation. Okay. How to do Fleming's left hand rule in exam without looking like you're cheating? You just don't look at your friend lah. You just focus on your own. Anyway, a quick rule, right? Since electromagnetic induction is not tested, in the exam, you just need to remember you got 2 rules. One weapon on each hand. Fleming's left hand rule on your left hand, right hand grip rule on your right hand. So you can walk into the exam with these 2. Okay, then you'll be safe. Don't confuse your Fleming's left hand rule and use your right hand. It'll give you a wrong answer. Okay. This one is obviously about Fleming's left hand rule. Your index finger, which is magnetic field, should be pointing from left to right. What does dot mean? Dot means that the current is coming towards you. So it's like your middle finger, you're pointing it at yourself. Okay, so where's the force? The force is upwards. Therefore, answer should be C. Okay, question 40. Here we see secondary. This is called a magnetic relay. If you're not too sure what that means, show you another diagram. So this under electromagnetism, under the various applications. So you see this thing called a magnetic relay. Basically, you're using a smaller circuit to control a bigger circuit, right? So here the high current does not switch off, right? So what's the issue? What can we do to make sure that we can attract this here? We use a stronger current, so you get a stronger electromagnet, which is then able to attract your flexible iron strip this way. Then you can break off this contact point. then your high current secondary circuit would stop flowing. Okay, so you're always using the primary to control that secondary. Okay, so that will be all for the MCQ. I know it was a bit fast, but time constraint. Okay, now time is around 8:47. For those that want to ask questions, you can ask now. If not, I will resume at 8:55. But before I answer your question, I'm going to go for a quick break as well. Okay, so once I'm back, I'll answer any questions that I see in the chat. Okay, 8:55, we'll go through the second paper. All right. Okay, so let's spend the next half an hour or so discussing the question here. Okay, same thing. Feel free to ask questions in the chat. I answer as much as I can. Okay, so I would need your help here, understanding that I can't answer all the questions. Okay, now first question is about a hydraulic system. This is very straightforward. This is 3 marks, difference between mass and weight. Okay, calculating force and calculating distance. Okay, these two formulas you should know for your hydraulic press. The only thing you ever need to keep in mind, right, is that the pressure in the hydraulic press is always constant. Okay, so you can either do F over A. Okay, in this case, I do work done is the same. There's one more, which is volume, right? So for those that are not very familiar with the hydraulic press, okay, so if you refer to the notes portion here, you're wondering what is this? This is just the curated notes, the soft copy version. Okay, so if you buy the hard copy, you will just get it in a booklet. Okay, so there are 3 formulas here. Okay, you need to know all 3 when you're solving hydraulic press. Okay, these 2 essentially they're dealing with the same idea. This one is saying that the volume of water that's passing through is the same. This one is saying that the work done is the same. So force times distance. Okay, then that's how you should be solving your part B and C. Okay, assuming that there's bubbles inside, you need to know that the high pressure will cause the bubbles to be compressed. So if I'm pushing down this side and there's bubbles, this side won't go as much because the bubble decrease in volume. So the volume of liquid here pushing it up will be less. Okay, so that's just one new situation that I want you to be aware of. Okay, question 2. There's only 2 principles you need to memorize in our entire syllabus, which is principle of moments and principle of conservation of energy. If you see this question in the exam, just write down the principle straight away. Okay, don't really care which question is at, just complete the definition question first. Okay, GPE to KE, I think this is pretty straightforward. There shouldn't be any thermal energy because it's a frictionless surface. For part C, when we want to determine the speed of the ball, right, notice that the mass is not given. So even if we are doing a conversion from mgh to half mv square, we actually do not need the mass. Okay, why do I say that? It's because when we are dealing with mgh and half mv square, you see you can actually cancel out the mass. So the mass is irrelevant. The only thing I'm caring about, right, in terms of conversion to KE is the height in which I'm dropping from. Because if I do V equals to square root 2gh, I'll actually get the velocity. So I just need the height to find the speed. Okay, then assuming that the ball travels here, right, work done against friction, F times D. F is given, D is given. So F times D, where did this energy to do work done against the friction come from? Where was this source of energy? The source of energy is the KE, but the KE originally came from the GPE. So what I did was that I just used the GPE directly. I know it's 10 meters. I know gravity is 10. I find the mass to be 3.3 kg. Okay. Anyway, if you prefer to do half mv square equals to work done against friction, you can as well. Your v square will be 14.1 square. Okay, I just preferred to use mgh because the values here are cleaner. So my SF is a lot more straightforward. If I use 14.1, it gets a bit messy there. Okay, that's the only reason why I prefer to use mgh. Okay. Next question, question 3. This is an adapted question from your 10-year series. So you need to realize now, right, Cambridge is not so much into regurgitation of content, but they're really trying to get students to see and apply their knowledge in a real world context. So for all the gamers out there, right, you know those like Aftershock PC, then they got all the cooling system, right? All the cooling processes are within your PC or the fan inside is all meant to cool down your processor. Because when the electricity runs through the nodes inside your processors, it heats up, right? And you don't want your processor to spoil, so you need to cool it down. So one of the technology that they have designed is using a cooling fin, all right? So what this cooling fin does, right, is that it helps to get rid of heat. How does this design help to do so? Okay, firstly, it's made of metal, good conductor of heat, conduct heat away efficiently. Convection, because you see these spaces in between. These spaces allow the movement of air, and hence we can set up convection current. Lastly is black in color because I'm trying to emit radiation away. So all the processes here helps to dissipate heat efficiently. So don't go into the exam memorizing conduction, convection, radiation. You kind of need to be able to apply it as well. Okay. Can we say good radiator instead of good emitter? You could, but I would always prefer to stick with the terms emitter and absorber because that is slightly more accurate. Okay, radiator, is it absorbing or is it emitting? Not too sure. But if I say emitter, I know for certainty I'm trying to get rid of the heat, right? Okay, drawing in convection current. Okay, the thing I want to highlight here is that when we are dealing with convection current, right, I think most of us understand how it works, right? But I think what we would need to pay attention to is how we explain it, especially with the keywords. So if you notice in the curated notes here, there are certain words that are bolded, right? Like liquid is heated, expands in volume, becomes less dense, and rises. So what I mean when we are talking about this chapter in transfer of thermal is that there are no formulas here, obviously, right? So no formulas, what does that mean? It means that really they are going to focus and double down on the keywords. So the reason why density is such an important word is because that is the reason why your liquid will move. So you have to mention density. Okay. Okay. Chai Mats, I hope you got your name right. I think you were the one that was chatting with me on IG, right? Okay. I don't understand the explanation for the vertical design. Okay. The vertical design is just, you see the spaces in between. So assuming we didn't do this design, right, and it's a complete block, right, the convection can only occur above it. But now, because we are allowing spaces in between the fins, convection current can form within as well. So we allow more convection current to be set up, hence transferring heat away more efficiently. Okay. Next question 4. This is about your thermal couple, right? So electromotive force. Okay, right. So this one. Okay, next, determine the temperature. Okay, so this one, I will always prefer to just think of it as proportions, right? So pure ice boiling water gives me 2.5 volt. What will give me 1.5 volt? So very simple, 100 degrees Celsius gives me 2.5 volt. What gives me 1.5 volt? 60 degrees, that's it. So you don't really have to memorize a formula. If you want to, you could, okay? The formula looks like that. But I honestly think you just use proportions, right? So you want to use you can use a formula, but why make your life so complicated, right? You just really need to remember proportions, then you'll be fine. Okay. Now they place the cold juncture in negative 150. Same thing, by proportions, what's your voltage reading? You know that per 100 degrees Celsius, you get 2.5 volt. Now it's from negative 150 to 100. So the range now is 250, right? So your voltage should be 6.25. Okay, so it's just going by proportions. That is how your thermocouple works. Okay, state 2 advantages. This one you just need to go and study. Should be in your notes. Okay, amplitude, pretty straightforward. Just take note, SI unit. This is also an adapted question from your 10-year series. Okay, so I know a lot of you might be writing 1.5. Hey, wait. 1.5 cm. 0.015 meters. Okay, take note. I need to change this data. Okay, so make sure you give it in your SI unit. Next, period of a wave, make sure you get your definition right. How do we find frequency? 1 divided by period. How do you know one period is 0.8? One complete wave, 0.8. Okay. Point B is 50 cm to the right of point A. What does that mean? You pay attention to the graph right now, right? You take a look at the diagram. You see at 0, this is where the first graph A started. But at B, right, it only started at this point. Okay, what does this mean? It means that between point A and point B, they're actually 1/4 of a wavelength apart, right? Because one period, it's 0.8. Instead of starting at 0, point B only starts at 0 at 0.2. So 0.2 over 0.8, they are 1/4 of a wavelength apart. Okay, so if they are 1/4 of a wavelength apart, that means one wavelength is 50 cm times 4, cause 50 cm apart, right? Then one wavelength is 1/4 times, so you want a full wavelength, so 200. Then V equals to F lambda. That's how you prove that the speed of the wave is 250. Okay, the reason why it could be other values as well is because they need not be 1/4. They could be 1 and 1/4 apart or 2 and 2/4 apart. Okay, then that would slowly push the value up more. Okay, and those are all possibilities. Okay, 0.2 for B. What do you mean 0.2 for B? Or point B, or why is it 0.2 apart? You just need to, okay, if you don't want to look at the starting point, you look at the crest, right? The highest point. Point A reached the highest point at the 0.2 second mark. But point B only reached the highest point at the 0.4 second mark. So they are obviously not in phase, right? They are two separate particles that we're discussing here. So how far are they apart? Okay, they are apart based on the graph analysis. It is 1/4 of a wavelength apart. And since the question told us that it's 50 cm, 1/4 of a wavelength is 50. I know my one wavelength is 200 cm. Okay, so here, therefore, it should be 250 per cm. Okay, cost times frequency. Okay, if not, let's take a look at question 6. This is a question on refraction. Okay, so value of A, do you see what's the annoying thing you have to take note of here? Okay, so what you will need to look out for here is instead of this 60, what must we tell ourselves? It's 30. I only care about the 30s because it's between the normal and the light ray. Okay, so here we know that the refractive index is 1.5. Okay, it's sine I over sine R, but more accurately, we don't really care about I and R. It's really about the angle in the air over the angle in the medium. So sine A over 30. Okay, so if that's the case, you should get a value of 48.6. Okay, if you do sine 30 over A, right, you get like 22.7. And that's not possible. Why? Because from denser to less dense, the light ray is supposed to bend away from the normal. You always expect A's value to be bigger than 30. So you need A to be the numerator. Okay, in any case, I always encourage sine air over sine medium. You come from my lessons or my crash course, you will know what I mean. Okay, so it's sine air over sine medium. Okay, next, value of B. So value of B is such that it allows the refracted ray to be 90 degrees. We know B as the critical angle, right? So we use the formula n equals 1 over sine C. We know that the critical angle is 41.8. Two conditions for total internal reflection: traveling from optically denser to optically less dense. Angle of incidence must be greater than the critical angle. Okay, state the value of C. This is C, not critical angle, this is C. 70, 70, right? Cause total internal reflection. Okay, if I use something of a higher refractive index, the angle B would be lower, right? Because sine I over sine R. Okay, largely, one application is always about the optic fiber. That's the only one that we learn in our syllabus. Okay, so that's why our internet is so fast now, because we use optic fiber. Last time when I was playing Maple Story, it was like some copper wire. So the thing download for a few days. Then I finally get my file. By the time I download already, I don't want to play already. Okay, but now optic fiber so fast, even faster 5G soon, right? Okay, now question 7. State two safety features here: 3-pin plug, okay, and insulating casing. Okay, so this one I think is pretty straightforward. Power, voltage, find current, P equals to VI. I think I don't have to explain this. State fuse rating, it has to be higher than the current. Okay, now if you put 4, can or cannot? Theoretically can, but I want to show you the reason why I put 5. Okay, it's because by right, as a physics student, you should know that when we are dealing with fuse, right, when we're dealing with our safety devices, okay, actually there are some more common fuse rating. You realize there's no fuse rating of 4, so that's the reason why I put 5. Okay, because I want to keep it to my common fuse rating, right? If not, in part D, we want to cap the power loss at 40 watts. So I'm using P equals to I squared R. If you're thinking, what is P equals to I squared R? Why are you making life so difficult? Okay, the reason is because we can also choose to use P equals to VI. That's fine, right? Okay, what am I doing? So I need a highlighter. Okay, we can just use this formula, and then we also use V equals to IR to solve the question. But if you want to be faster, you want to big brain energy, right? What do? You see, how did I get P equals to I squared R? I just sub in V equals to Ri. So instead of V, I put Ri. So it's Rii. So I square R. V square over R is the same thing. I'm just subbing in I equals to V over R. That's how I get V square R. So this is more straightforward method. Not say straightforward, more faster. I'll say faster, right? Faster method to calculate my unknown resistance. Because here, if I use I square R, straight away I know my R. I just have to take my power divided by my current square. I already have current that I found in part B. The question already gave me power. So I'm able to find the resistance straight away. Okay. For part E, all right. So if we take a look at the calculations here, right? 2 toasters were used. So 2, and then what's the power? The power. Go back to the question. 900, right? But I need it to be in kilowatts, so 0.9. 5 minutes daily. So that means 5 over 60 of an hour for 30 days, right? So it's 4.5 kilowatt, okay, times 15 cents, okay, it will be approximately around this value, okay? Question section B. So the trend for section B nowadays is you realize that they tend to give you a bit of nonsense, right? Something out of context. You might not have seen it before. So I don't know how many of you actually have traveled, like COVID, right? Can't even travel, but maybe before that, if you've ever been to the Iceland region, they actually have this very famous thing known as the Northern Lights. Okay, it looks amazing in person. I say until like that, but I actually never been there before. Okay, cost very expensive. But okay, the thing about Northern Lights and why it's so unique is because it has a very nice array of colors. Okay, and what is it caused by? It's caused by powerful electromagnetic waves. Okay, so as mentioned earlier, right, we need to know the properties of EM wave. So if you look at the article and you extract certain portions, you'll notice that they do mention how there's transfer of energy and how EM waves actually travel through your vacuum. Okay. So a possible deduction why we see a variety of colors is because when the electrons collide, right, the energy transfer will vary, producing colors of differing frequency and wavelength. That's why we see different colors. That's why to us, the Northern Lights look so beautiful. Okay, it's because different spectrum of colors were shown. Okay, 2 EM waves with higher frequency than visible light, anything from UV to X to gamma, and you state their uses. Okay, this one is 3 marks. Okay, you have to score this in an exam. Just need to revise. Okay, then we also see the dispersion of light. Okay, so why does dispersion of light occur? It's because of refraction. Does red or violet have a greater wavelength? Okay, so this one, you can go and take a look at the explanation, right? So when we have smaller wavelength, okay, by right, the speed would decrease more. Okay, since the speed decreases more, because n equals to speed of light over speed of light in medium, when it slows down more, your angle of refraction will increase. Okay, and when that happens, okay, since they are of shorter wavelength, okay, they slow down more, they experience more, cause angle of refraction increases. Okay, that's why you get these colors for violet and blue here, because they bend the most, while red bend the least. They bend the most here because they have the smallest wavelength. Okay, so red has longer wavelength. Another place you do see this appearing again, right, is under your EM waves as well. Coto mate. Next shutter. Here. So you take a look here, right? Under your electromagnetic spectrum, they actually also show you the wavelength of your blue versus red. While they are all categorized under visible light, okay, red color actually have lower frequency than blue. Blue have shorter wavelength than red. Okay, so this is something that you might want to pay attention to. If you are interested, you can always Google and YouTube more on how this phenomenon works. Okay, this is called dispersion of light. Okay, question 9 is one of my favorite questions because it really tests how well you know your circuits. If you are only at a decent level, at most you can solve till D. Okay, if you can't even solve D, it means you're in trouble. If you can solve E, you're quite godlike. Okay, but let's run through this question together and take away the key learning points here. Okay, first one, we want to find the current I1 and I2. Okay, so how do we find I1 and I2, right? What we do here is we need to recognize that the voltage each of them receive is the same. Now, the question told us that the ammeter here experiences a 0.5 ampere reading. So V equals to IR, right? So I is 0.5, R is 6. So I know that per branch, I experiences 3 volt. So 3 volt for my third branch, my first and second branch should be 3 volt as well. So I just need to do the same thing. If I know it's 3 volt equals to I times R, right? R is 2 ohm. How do I find I? I'll know that it's 1.5. The current I2 is 0.75. Okay, so the key takeaway is that the voltage across each branch is constant. Okay, that's how I find I1 and I2. Total current, I just need to add up all 3 currents. This is a free mark, 2.75. Find the reading on the voltmeter here. Now, 3 volt, 3 volt, 3 volt in the second circuit. So this entire circuit here is 3 volts. I mean, this parallel portion of the circuit is 3 volts. Take a look at wire Z, right? So what wire Z does is that it's actually a short circuit. Why do I say that? It's because if you're thinking, should I pass by 3 ohm or should I go through an empty wire, right? Path of least resistance, right? Everybody's lazy. We want the easiest path in life. Obviously, nobody's going to go through the 3 ohm. We're going to take the easier way out through the wire. So when that happens, this 3 ohm exists as if it doesn't exist. If this is a light bulb, the light bulb will not work. Right? It will not light up. That's why it's called a short circuit. So essentially, if this is 3 volt and this is 6 volt, what this tells you is that this circuit is 3 volt. Which means if you put a voltmeter in parallel here to measure one of the branches, it will give you 3 volt. Okay. Part D, determine this resistance then. Since I know my total current, which is 2.75, and I let X be the unknown, right? I can calculate my effective resistance, right? I just need to play around with the numbers a bit. Why do I say that? Because I know V equals to IR. I know my voltage is 3. I know my current is 2.75. I can already find the total resistance. My total resistance is 12 over 11. Then I put it back in this form. 1 over R effective, right? Equals to 1 over R1 plus 1 over R2. What is my R effective? My R effective is essentially 12 over 11. What's my R1? If you go back to the circuit, it's 4. So it's 1 over 4 plus 1 over X. Then I solve for X. Okay, X would be 1.5. Okay, lastly, when I get rid of wire Z, what happens now? When I get rid of wire Z, my current is now forced to pass through the 3 ohm resistor. How does this change the game? Because now the 3 ohm is introduced, my total resistance will change to 5.18 because I'm essentially adding in a 3 ohm resistor to my circuit. Why do I do 12 over 11 times 2? Because here the voltage they receive is 3 volt. Okay. And then if you go and calculate the resistance here is also 12 over 11. So 12 over 11 plus 12 over 11. Okay. Plus 3, right? So my total resistance is 5.8. I find my total current. How does my current split? Okay, this is the most difficult part. So listen in closely. I'm almost done with the lesson. So if my current is coming in here, how much current goes to the top, to the middle, and to the bottom? The current needs to split in such a way that each branch will have the same voltage. So what I mean is this. I1 times 2 need to give me a same value as I2 times 4. And it needs to give me the same value as I3 times 6. Because each of them must have the same voltage. So my Ri or my IR has to give me a constant value. So you take a look at all these values and you want to calculate the ratio of what they are worth. Okay. I1 would always receive up to 3. I2 will always receive 1.5. I3 will always receive 1. Okay, if you're confused, right, make it simple. Think of this as current 3 times 2 equals 6. Okay, 1.5 times 4 equals 6. 1 times 6 equals to 6. So I need to make sure that my voltage is always the same. Okay, it need not be 6 volt because I do not know what voltage they receive now, but the ratio in which how the current split, it always split according to 3, 1.5, and 1. So I just need to take my total current divided by 3 plus 1.5 plus 1. That's how I'll get my reading in my ammeter. Because my ammeter reading is the 1. Okay, Now, if you're confused and you're like, Joe, what the hell are you talking about for E? I think it's okay. It's okay if you don't know this, right? Because this one's a bit more high level. Okay. If you're able to solve this, good. Okay, will it appear at O level? Unlikely lah. Okay, so if you really don't get E, it's okay. Don't beat yourself over it. But if you really understand what I said, it just goes to prove that you truly know your DC circuit. Okay, minimally, I need you to be able to solve up to C. Minimally. Okay, if you want to get A, most likely you need to solve D. Okay, A1, this is the level we're talking about. Okay. Okay, last question, question 10. Okay, earlier I know somebody asked me to explain DC circuits, okay, but I didn't do so because I wanted to do so here in question 10. So for question 10, right, we see a DC circuit, okay. The easiest way to break down a DC circuit is to understand what's happening on the each side of the coin, right? So here we have north to south, right? We have the current, okay. What this means is that A, we should experience an upward force, B, a downward force. How do I know upward, downward force? I apply Fleming's left-hand rule. Okay, so first question, this is always a question that is going to be tested. Why is a split ring commutator required? It's because it allows the direction of the current to be reversed every half a rotation. Okay, this one will always appear. Okay, trust me. So go and study what your split ring commutator does. Okay, next, explain what's happening in A and B, right? So we talked about how A experienced upward force, B experienced downward force. You use Fleming's left-hand rule to justify that. Okay, then that's how we justify, and therefore having a, therefore they will experience a clockwise movement. Okay, then explain why does the coin not stop at the vertical position is because momentum of it will bring it through. Okay, another question type that you will see a lot for electromagnetism, okay, is about the deflection of your particles. Okay, now take note, this one is positively charged. This is current. This is electron flow. Electron flow is the reverse of current. Okay, so what happens to the two stream of particles before and after they enter the magnetic field? Before they are entering, they're actually traveling in opposite directions. So opposite direction current will actually undergo repulsion. Okay, now once they enter, okay, the positively charged particle will deflect to the top while the negatively charged will deflect to the bottom. Okay, why is this the case? Is because of Fleming's left-hand rule once again. If you take a look at the diagram, okay, your middle finger here should be representing your current for the plus. Magnetic field is going into the paper. That's why the force of deflection should be going upwards. While electron, the current is reversed, force generated is downwards, therefore this way. Okay, so this is how you calculate deflection using Fleming's left-hand rule. Okay, and obviously if we reverse the direction of the magnetic field, the deflection will look different. Okay, and that's it. Okay, I know this one is not the easiest kind of questions. Okay, this one and this one. Okay, but you need to be comfortable answering part D and E. Okay, because they will appear, especially considering how electromagnetic induction is not tested anymore. Okay, you can almost guarantee that DC circuit will appear. So if by now you're still not very familiar with it, I highly suggest you spend some time, okay, to go and look through the questions again. Okay, if not, I'm pretty much done. I will leave the later to do a bit of Q&A. But just to wrap up today's session, just wanted to run you all through some of the stuff before you hit towards your O level. Okay, I always emphasize this and I say this again. If at this point in time you're still not familiar with your content or your concepts, I highly recommend you to go and revise those first. There's no point blindly doing practices for the sake of it if you don't even know your stuff, right? So if you don't even know what your DC motor, how it works, right? You cannot do DC motor questions. Okay, the more you do, the more demoralized you're gonna get. Okay, so no matter what, make sure you get your content right. I know some of you have a tendency to memorize formulas. Is that okay? I think memorizing formulas help you to get a quick start in terms of, okay, now I get my physics on track. Memorizing formulas only work to a certain extent because the moment the question gets a little bit more complicated, and if you only blindly apply formulas, you will not get far. So when you're studying your formulas, yes, you need to memorize them, but at the same time, you need to understand the context in which they are applied to questions, okay? So it comes with understanding your concept first, then trying it on questions, okay? Then I think the best way to check, okay, is you need to go and recall that knowledge to see if it's really in your head. And a very good way is to test yourself. Okay, if you have a group of friends, test each other, right? Quiz each other. What is the principle of conservation of energy? See if anybody gets it right. Okay. And I think that would be very helpful, especially when you're preparing to work towards your O levels. Okay. If not, okay, just a quick shout out. Okay, in case you're not aware, okay, we actually do crash courses. It's at a center near Yishun. So how the crash courses work is that within these 4 hours, we'll go through every single chapter in the syllabus. We'll talk about key concepts that you need to know of. We'll highlight commonly tested questions that we are expecting to appear in some form at O level, and we'll teach you how to solve it. So during this 4-hour session, you will receive a free copy of the curated notes, and then you will also attend the session and really learn from us directly because it will be a face-to-face session. Okay, for the physics one, there's only 1 slot left. It's on 2nd October and it's going to be an online session. So that one is a bit different because it will be in the comforts of your home. We'll mail you the notes in advance and then we'll attend the session, something like that. But of course, with a lot more practices and a lot more content revision. Okay, so the one I'm talking about is 2nd October from 4 to 8 p.m. Okay, I'll also be hosting the one on 18 September for chemistry 2 to 6. I think there's only like 6 slots left for this one. So if you want to see my face, please make sure you sign up soon. Okay. Lastly, if you don't need the crash course and you just want the notes, right, you can also make a purchase for it. Okay, but only if you need it. Okay, if your school notes are already sufficient, then you don't have to buy this. All right. Okay, that's all for today. Okay. Next, I would spend the next time to answer any Q&A. Okay, but I think for those that have no questions, I thank you so much, okay, for coming for this session. I really hope that y'all learned something today, and I hope that this mock paper practice have been helpful in getting you more ready for your O levels. Okay, so if not, that's it. Okay, have a good rest.